All right, today we're going to dive into something that honestly looks like it's straight out of a sci-fi movie. But I promise you, it's very real, and it's all grounded in some absolutely beautiful physics. We're talking about physics that literally saves lives. I mean, just look at this thing. It's this enormous 728-ton sphere of solid steel hanging from these massive cables way up near the top of Taipei 101, one of the tallest buildings on the planet. They call it a tuned mass damper, but really it's just a gigantic pendulum. So that's the big question, right? How on earth can a huge, swinging ball of metal protect a building that's over 1,600 feet tall from the unbelievable power of an earthquake or a typhoon? Well, the answer is just wow. And it all starts with understanding the basic rhythm of, well, pretty much everything. Okay, so to really get how this all works, we've got to start with the basics, the physics of things that move back and forth, over and over, in a really predictable way. We need to get a handle on the rhythm of motion. And that brings us to this key concept called simple harmonic motion. Now, I know that sounds super technical, but the idea behind it is actually really simple. Just think about a kid on a swing set. It's any kind of repeating motion where something is always being pulled back to its starting point, its center. This diagram here is the perfect way to picture it. You pull that mass down, right? The spring wants to pull it back up, but it shoots past the middle, and now the force pulls it back down again. You get this constant back and forth, back and forth. That is simple harmonic motion in a nutshell. Now, anything moving like this has this really important property called its period, and that's just the amount of time it takes to do one full cycle. For the swing to go all the way up, all the way back, and return to where it started. Hang on to that word, period. It's going to be a super important clue later on. And yeah, it's not just about springs. A pendulum, like the giant one in our skyscraper, is a textbook example of simple harmonic motion. It has its own natural, predictable rhythm, a period that it loves to swing at. Okay, so we've got it. Things have their own natural rhythm. But how does the energy from something like an earthquake even get into the building in the first place? Well, it travels in the form of waves. So what even is a wave? Well, a mechanical wave is really just a disturbance that carries energy through stuff. The best way to think about it is tossing a stone into a pond. The water molecules themselves are mostly just bobbing up and down, but that ripple, that energy, travels all the way across. That's exactly what's happening with seismic energy in the ground. And these waves basically come in two main flavors. You've got transverse waves, where the particles wiggle up and down while the wave energy moves forward. And then you've got longitudinal waves, where the particles get squished together and pulled apart in the same direction the wave is going. And you can really see the difference here. For the transverse wave on the left, just imagine you're shaking a long rope up and down. For the longitudinal one on the right, think about a slinky. You push one end and you see that compression wave shoot all the way to the other side. And get this, earthquakes actually produce both of these. And just like anything, waves have their own anatomy. The top point is the crust. The bottom is the trough. And this part, the amplitude, the height from the middle to the crust, is super important. It tells you how much juice the wave is packing. A bigger amplitude means way more energy. And for a skyscraper, that means way more danger. Okay, this is where it all starts to click. This is where the magic happens. We've got buildings that want to sway and energy traveling in waves. So what happens when two waves run into each other? Because this idea is the absolute heart of how you save that building. It's all about a rule in physics called the superposition principle. Again, sounds complicated, but all it really means is that when waves overlap, you just add them up. So what happens if the high point, the crest, of one wave lines up perfectly with the crest of another one? They join forces. Their energies add up and you get one single, much bigger wave. This is called constructive interference. And for something like a building, this is bad news. It's how small sways can become big, dangerous ones. I mean, the textbook definition is right here on the screen. It's the algebraic sum. Basically, it's just math. A wave with a height of, say, +2 meets another one that's also +2. What do you get? A new wave with a height of +4. Simple. Okay, but what if the opposite happens? What happens if a crest, a high point, meets a trough, a low point? What if that +2 hits a -2? Well, +2 and -2 equals 0. They completely cancel each other out. This right here, this is called destructive interference. And this is the secret weapon. All right, it's time to put all these pieces together. We've got our simple harmonic motion, we've got wave energy, And now we've got this amazing trick of destructive interference. Let's see how it all comes together to save a skyscraper. Okay, so here's the play-by-play. Step 1, an earthquake hits. Its energy makes the building start to sway back and forth at its own natural frequency. It's period. Step 2, now remember that pendulum? The engineers are smart. They have tuned it so its own natural period is exactly the same as the building's. Step 3, as the building gets pushed to the right, that huge pendulum, because of its inertia, swings to the left. Step 4, that swing creates its own force, its own wave of energy that's perfectly opposite to the building's sway. And step 5, well, what happens when two opposite waves meet? The pendulum's wave and the earthquake's wave. They collide. The crust of one hits the trough of the other. And boom, destructive interference. They literally erase each other. And the result? It's this. You have a skyscraper that stays incredibly stable, just gently rocking, while the Earth itself is shaking violently underneath it. All because this giant pendulum is essentially dancing against the earthquake's rhythm, canceling out its destructive energy. And that is the big takeaway. You see, it's not about just trying to stop the motion with brute force. That would be impossible. It's so much smarter than that. It's about using motion to cancel out motion. And that just leaves you wondering, right? We use this exact same principle in noise-canceling headphones to erase sound waves. We use it here to erase earthquake waves. So if we can master these fundamental laws of physics to protect our cities, what other huge challenges are out there that we could solve just by understanding how to make waves disappear?